Okay, 3, 2, 1, it's jam.
What's up, science fam? In the last video, we talked about Alfred Wegener, continental theory. In this video, we're going to talk about the theory that explains exactly how the continents moved. So, my name is Sir Ramon, and this is Science with Sir Ramon. Do this. So, the theory we're talking about this time is the seafloor spreading theory. It gives a much better explanation for the movement of the Earth's crust or the surface. And it all starts on the ocean floor. And the guy who suggested it is Harry Hammond Hess. So he's a geologist and also a US Navy officer. So these two occupations combined gave him the best possible way of being able to see the evidence for this theory. Because he's a US Navy officer, during the World War there was lots of data that was available about the ocean floor from US submarines and US ships, Navy ships. So he took this data and he saw some patterns in them that allowed him to come up with this theory. So what's the theory about? What are some of the details of the theory? First, there is the concept of a mid-oceanic ridge. So this is an oceanic ridge at a divergent boundary. It's a mountain range underwater. And it's characterized by high seismic and magmatic activity. It's like a huge gash or crack in the ocean floor. So it's very, very, very long, kilometers long, and it constitutes some of the longest and highest mountain ranges in the world if you count from the base of the mountains up to the tip without counting sea level, of course, because it's sea. So these mid-ocean ridges are very important in seafloor spreading. So the ridges are where the magma comes up and out onto the ocean floor. And as it comes out of the ocean floor, it spreads along the crust. And at the other side of the crust, at the edges of the crust, we have what we call subduction zones. So subduction zones are areas where denser crust gets taken under the crust, taken under other layers of crust. So it subducts or it sinks under less dense types of crust. So you can see on both sides, the oceanic crust, which is very dense, gets subducted down into the mantle. So again, we have the mid-oceanic ridge in the middle and subduction zones on the edges. Now, what drives the crust to these subduction zones? What's the driving force for the crust to be moved from the oceanic ridge going to the subduction zones? So one of them is what we call convection currents in the asthenosphere. So again, in the asthenosphere, it's very hot and it's plastic, meaning it's solid but flowing. So because of that, there are currents of energy transfer. Now, when this energy is transferred to the Earth's surface or to the crust, then the crust itself moves along the currents and flows with the currents. Your ridge push, on the other hand, is the pushing of the weight of the mid-ocean ridge. So the mountain range on top of the mid-ocean ridge, it actually pushes on the rest of the crust so that it tries to move away from the ridge, especially since the ridge itself is spewing out more lava that's hardening into more rock. So it continually pushes the rest of the crust towards the subduction zones. Now, when we look at the subduction zones themselves, they also have a certain driving force on them. They have what we call a slab pull. So it pulls the entire slab of crust as it gets subducted underneath the other crust. So the subducted crust pulls whatever it's connected towards the subduction zone. So again, we have the ridge push on one side, the slab pull on the other side, and the general movement is along a convection current. So we have three main driving forces. Now, where's the evidence of this seafloor spreading? How can we say that there's seafloor spreading aside from, huge oceanic ridges? So first type of evidence is the age of the rock near the mid-oceanic ridge. So rocks are younger the nearer they are to an oceanic ridge. And as you go farther away from the ridge, it gets older. Now, that is supporting the theory because the mid-oceanic ridge, as lava comes out and it becomes new rock, you find the younger rocks right next to the ridge. Now, the older rocks get pushed away by the motion of the crust so that they're found farther from. Next, we have the magnetic stripes formed from the mineral magnetite. Now, magnetite can exist in small concentrations in oceanic crust, and magnetite forms polarization patterns. See, the Earth's poles, the north and south magnetic pole, can flip over geological time. And when they flip, the polarization or the polarity of the mineral magnetite can also flip. So these bands, the light and dark bands, are just symbolize the polarity of the magnetite that are found in those areas. Now, the magnetic stripes support seafloor spreading because they are symmetrical with respect to the ocean ridge. So since the seafloor spreading theory is trying to suggest that the ridge is forming new crust and spreading it across to the other sides, the symmetrical patterns are actually showing that since they're symmetrical, it's coming from the mid-oceanic ridge. The new crust is coming from the mid-oceanic ridge itself. So these very long ridges form not just short cracks, but very long ridges and huge pieces of crust, because these pieces of crust are what we call plates. So that leads to the theory of plate tectonics. Now, Earth's surface is divided into huge plates that drift around over geological time. So this is the result of what we call a scientific revolution, putting together Wegener's theory of continental drift, which was rejected at first, but with seafloor spreading as the correct mechanism of moving the continental crust, put them together and add together the data collected over many years, many decades of geological study. We now have a much clearer and more complete picture of how the Earth's crust or the Earth's surface moves along geological time. So this theory of plate tectonics, it's geology, biology, a lot of different disciplines of science over many decades coming together to put forth something that explains something much bigger than us. So let's get down to the details. We have the plates. These are actually chunks of lithosphere. Now, the lithosphere, as we discussed before, is a rigid rocky layer. And because it's rigid, the lithosphere tends to bend or to break under pressure. That's why it broke apart into plates instead of flowing like a fluid does, because that's what the asthenosphere does. It's plastic, meaning it's solid, but it works like a fluid if you look at it in a geological time scale. So again, lithosphere bends and breaks, asthenosphere flows, and that results in a fluid asthenosphere and a cracked apart lithosphere. So your different plates move in different ways and at different rates, and that causes different types of plate boundaries. And these different types of plate boundaries give different geological features, which you've already seen when we discussed Earth materials and processes. So your divergent boundaries, such as your mid-ocean ridges underneath the sea, form rift valleys and normal faults. Your transform boundaries are when your plates are horizontally moving against each other. So we have fault lines and track-slip faults. Your convergent boundaries, on the other hand, are a bit more interesting because there are three main types of convergent boundaries. We have Oceanic-Continental Convergence. Now, this is the type of convergence where you have oceanic crust, which is more dense, and continental crust, which is less dense, meeting each other. Now, since oceanic crust is more dense, that's the one that gets subducted. It sinks because it's more dense. So once it sinks and partially melts, the sunken part partially melts because of the heat pressure, that part, melted part, gives magmatic pressure to the continental crust above it, resulting in what we call volcanic arcs. So again, in Oceanic-Continental Convergence, we have usually trenches and volcanic arcs. We see a lot of these types of convergence zones in the Philippines. We have a lot of volcanic arcs near the coastlines and lots of trenches just off our coast. Alright, next we have the Oceanic-Oceanic Convergence. If it's both oceanic, generally the older crust is more dense because it's cooler or because it has more heavy minerals. So the older crust tends to sink, and that's what partially melts. And that can create a volcanic arc in the ocean. So we call that instead an island arc. Oops, I wanted to move my face. No, move my face instead. Alright, so your island arc over here, there we go. Island arc is here, and it also forms a trench. Now, arcs that come up in the middle of the ocean, like your islands in the Pacific Ocean, these are most likely island arcs. Most of them are island arcs that form due to the convergence of oceanic crust. Next, we have continental and continental convergence. If it's happening on land, the older crust sinks under, while the upper crust tends to fold up, fold into mountains. So we have mountain ranges that form fold mountains, usually high plateaus. So your continental crust is generally of a certain age. If you look at your oceanic and continental convergence, there's a takeaway from this where we relate the age of your continental crust and your oceanic crust. The oceanic crust usually subducts under continental crust. What do you think is older, oceanic or continental crust? I'll leave that, guys, to you in your brainstorm. So some things break apart. But even if it's difficult, even if it's not something you're used to, change isn't always bad. So just like Hutton changing the minds of people in the 18th century, sometimes change can lead to growth and development. So even if you're used to, for example, seeing a certain someone, seeing your classmates every day, and now there's a lot of changes, we're on online classes, sometimes that can lead to different types of growth, like personal growth. Maybe you're taking up different hobbies, or you're trying new things now that you have more free time to yourself. Okay? So hopefully I don't give you too much workload so that you have more free time to develop yourself. I will leave you guys here. I'll see you guys in the next.
Party's over.